In this video, we're going to look at the normal distribution as a specific type of continuous random variable probability distribution. And so we write that our random variable x is distributed normally with a mean. Normally we'll have a number here, and here they actually put the variance. So you need to be really careful about this when you are reading values from here. We don't actually use the variance, we use the standard deviation. So if you have a value in here of 4, okay, so if theta squared, sigma squared is equal to 4, then your standard deviation is in fact 2. Now we look at the normal distribution because it's one of the most important distributions that we have. It fits many natural phenomena like heights, IQs, blood pressure. And for large values of n, for many trials of other sorts of distributions, you can actually model the distribution that you get using a normal distribution. Now, the normal distribution is often described as having a bell-shaped curve, and this is the bell-shaped curve here. And the bell that it's talking about is like the little Christmas bells that hang on the Christmas tree. That kind of bell there with the little dinger that hangs out and the little thing that you hook over the tree. So that's the sort of bell that we're talking about, with a bell-shaped curve. And what we have with a bell-shaped curve, we have the fact that the curve is in fact perfectly symmetrical, which means at its highest point you've got 50% of the data on one side and 50% of the data on the other. And that makes this particular x value down here, this particular x value here, as the mean, the median, and because it's underneath the highest point, it's also the mode for the particular distribution. So let's have a look at the normal distribution in a bit more detail. So the shape of the normal curve is based on the function e to the power of negative of x squared. And we have what we call a standard normal density function, and this is its formula here. And you can see that it just has a couple of transformations here by a constant that make it very slightly different from its original function on which it's based. So our standard normal density function, this one here, is a function that we'll come back to later when we look at the standard normal. But the general normal density function, so the general normal distribution that you'll be working with quite a little bit, actually has a formula that looks like this. Now, on the formula sheet for the exam, it has the formula, and here it is here. So it's actually, we've got an integral here, but this is the formula in here. And all I've done is pulled apart the different components. So you can see in yellow that we've still got the standard normal distribution, but if we've got a different mean, and we've got a different standard deviation for our normal distribution, that they do in fact act as transformations to this original function. So the mean is up here, and what's happened in this formula here, we've replaced x with x minus mu. And so what that means is that the mean is a translation left and right. The one on standard deviation at the front here is a dilation factor, a vertical dilation factor, by a factor of 1 over sigma. And finally, we also have up here with the x, so squeezed in here, we have 1 on sigma squared multiplying the x. So we also have a dilation factor here, and this is a horizontal dilation factor, and it's dilated by a factor of sigma squared. And so hopefully you can see, if we look down at the way that the formula is written at the bottom of the screen, the mean shifts the graph of the function left and right, so it moves it left and right. The one on sigma at the start changes the dilation vertically, so it's going to stretch the graph upwards or shrink it downwards. And the sigma underneath the x minus mu is also going to dilate it, but it's going to dilate it horizontally. So it's going to pull the graph of the function in and up or down and out. Let's have a look. So let's look at these graphs at the top here first. Let me just put this down a little bit. Okay, so our first one we're going to look at is the blue one. So this is a mean of 0 and a standard deviation of 1, because 1 squared is 1. So the mean of 0 means that the graph, the mean will be sitting at 0. It's shifted across and it's sitting right at 0, and you can see that it is. The peak of the point is sitting over 0, and the standard deviation is 1. And I'll talk a little bit more about that in a sec, but you can see that's the size of it when it's 1. For the second graph, our mean is -2, and so the peak of the graph is sitting over -2. So can you see that the blue one looks like it's come across 2? And the standard deviation, remember that 4 is in fact sigma squared, so our standard deviation is in fact 2. And so our standard deviation is a larger value than the 1, and so you would expect your graph to be further stretched out and shrunk down a little bit, and you can see that that's what's happened here. And in the final one, our mean is 2, so you can see that it's situated over 2 on the x-axis, and our standard deviation is 1/2, and it's made it skinny and tall. So you can see that the normal distribution, let's have a look down here, comes in all different tall and skinny ones, short and wide ones, but they are all normal distributions and they all have the bell-shaped curve. So let's have a look at this bell-shaped curve in a little bit more detail. So I've already mentioned that the mean sits right underneath the peak of the graph, but what we're going to do is we're going to actually estimate the standard deviation from the shape of the graph itself. So if we start at the mean and we go out 1 standard deviation this way, and we go out 1 standard deviation in the other direction, we are what we call, just mark in the mean, we are what we call 1 standard deviation above the mean and 1 standard deviation below the mean. And at this point here on the curve, you should be able to see that if you look at the curvature of this curve, that at the minute it is curving downwards, and then it turns and it starts to curve upwards. So what you actually have right at this point here on the graph is in fact a point of inflection. And this is how we identify what the standard deviation is, obviously approximately, on a graph. And so you have the 2 points of inflection just there on either side of the mean. So it's where the graph stops curving up and starts curving down, or stops curving down and starts curving up. So let's have a look at finding the mean and standard deviation for these particular graphs here. I'll just make them a little bit bigger for you, hold on. Okay, so what I'd like you to do, remember the mean sits the x value that sits right underneath the point, the highest point on the curve, and the standard deviation is the distance from the mean across to where that point of inflection is. Have a go with these and see how you go. Write your answers and I'll give you my answers in just a sec. Okay, that's what I got. How did you go? Picking the point of inflection can be a little bit difficult. If this was an exam question, I would be thinking it would be a multiple choice question with some options for you to choose, which will make it more easy to pick whether it's actually 3 or 2.5 for the standard deviation. So finally, I want to have a go at a question that asks you to look at the formula for the probability density function. Look at the formula for the probability density function, identify the mean and the standard deviation, and then describe the effects that the mean and the standard deviation have on the graph. So it's asking for the transformations. Okay, so here's the formulas that I've given you. Here's the formula from the formula sheet to help you. Just be careful about how the standard deviation appears here, either included in the brackets with the squared or just the brackets squared on the top and sigma squared on the bottom. Have a go and see if you can identify the mean and the standard deviations. So the first one, you can see that where the sigmas are in the formula, you've got an 8. So the standard deviation is 8. And what the standard deviation does is this one dilates it vertically by a factor of 1 on 8 because it's in the denominator of the fraction here. So if you remember back to my original formula, you could have just as well had it as 1 over 1/8, 1 over 1/8, 1 over 8 times the standard formula. So that's where the 1/8 comes from. And here, this is sigma squared. And so you have your x divided by sigma squared. So you're dilating horizontally by a factor of the inverse of that, which is 8 squared. The mean has a plus in front of it, and you'll notice on the formula sheet that there's a minus sign in front of the mean, which means that our mean is in fact minus 10, which means it translates 10 units to the left. For this final one, normally our sigma is just on the bottom of the fraction in the denominator with a 1 on the top, but here we've got 3 on 2. The only way you can end up with 3 on 2 here is if you are dividing by 2 on 3. Okay, let me do that for you here. Okay, so you've got 1 divided by 2/3, which you can write as 1 divided by 2/3. When you divide by a fraction, you change the divide to multiply and you invert the fraction here, you turn it upside down. So now you've got 1 times 3 on 2, which gives you 3 on 2. And that's why sigma here is 2 over 3 when it appears to be 3 over 2. The other thing that we've got up here is this is a different version to how it's written here. Only the top line is squared. Using that bracket, what you've got on the bottom is in fact 2 squared. So if you put that back into the bracket, that's actually 2 squared. So if you put it back into its bracketed form here, you would end up with a 2 on the bottom. How did you go with those? So remember, on the formula sheet, you've actually got the formula for your normal distribution if you need it. And if you are going to have a normal distribution question on exam 1, where you don't have your calculator to work it out, you can be asked questions about the mean and the standard deviation because the information is on the formula sheet for you.